ARFTG thanks Dr. David Root for presenting the keynote talk at the 94th ARFTG Microwave Measurement Conference. Sadly, due to technical difficulties, the audio does not begin until slide 6.
Strange phenomena and the incredible power of quantum mechanics to improve how we do quantum computation. Now, is this hype? I mean, you've probably read all kinds of things in the media. Quantum computation is approaching the peak and the hype curve. And of course, it could tunnel through the barrier and fall into the trough of disillusionment, or eventually it might reach there. So is it real or is it not? Well, on my way to Europe to talk actually to some of the researchers, this headline came out where Google claimed to have actually demonstrated what they call quantum supremacy, performing on a quantum computer a task that would take much, much longer than any supercomputer in existence, and then ultimately of any supercomputer that's possible. And while we now call that quantum advantage, there's been some debate with IBM as exactly how much faster. The real experts in the world pretty much agree that this is, in fact, a very significant technical milestone. The algorithm that they used was irrelevant and didn't do anything practical, but it was a true demonstration of the fact that quantum computation can really be proved to be superior in, at least in this case, artificially contrived calculations. So with that introduction, let me start introducing the foundational concepts, and there are a couple of key ones that I've enumerated on the slide that you should be looking out for. And I won't be able to go into all this in depth, but it's to give you a flavor of really what's behind the science and how microwaves can enable the application of these principles. So we know about a classical bit. It can take one of only two values. And a quantum version, the fundamental unit of quantum information, can, in a sense, be in a superposition anywhere in between. Now, that's kind of frowned upon by physicists. It's really saying that the state of an ideal two-level quantum mechanical system is in a complex superposition of two of the basis states. So the symbol ket 0 and ket 1, they're not the number 0 and number 1. They represent unit vectors in a two-dimensional space, just like x hat and y hat in the two-dimensional plane. But because quantum mechanics is linear, the representation of the quantum state, which is the most you can know about such a system, is this superposition. Alpha and beta are complex numbers. It's a complex vector space. And there's a constraint on the sum of the absolute square of the superposition coefficients given over here. So because of that, it's possible to represent the state of a qubit as a point anywhere on the surface of a sphere of radius 1. And then we can parameterize that point in terms of the standard spherical angles, theta and phi. And this is called the block sphere, and it's very useful for visualization, at least as far as one qubit goes. Now, just because we may know the state of a qubit doesn't mean we know what we would get if we actually look at the qubit. And here is one of the great mysteries of quantum mechanics. If we prepare a qubit in this state and we then make a measurement, we'll get one of only two values. So even though the state can be anywhere on the sphere, when we look at the qubit, it collapses immediately to either the 0 state or the 1 state. If it's a photon, you get either vertical or horizontal polarization. If it's a spin, you get either spin up or spin down along the z-axis, nothing in between. And even if you were to prepare the same state again, exactly the same state, and you made the same measurement, you may get a different result. So philosophically, you could say that even violates the old principles of the scientific method. If you set up an experiment, you expect to get the same answer. Not true. Quantum mechanics and nature is fundamentally probabilistic. It's not a question of ignorance of initial conditions or other bits of information. But the point is, when you make a measurement, you retrieve only one single classical bit of information, 1 or 0. Now, you can, by repeating the same experiment thousands of times, estimate the probability of getting the particular result that you've gotten, and those probabilities are related to the absolute square of the coefficients. Now, where do microwaves come in? It's when we go from the ideal qubit to a physical representation. In this case, we'll look at the Josephson junction shunted by a capacitor. The X is a symbol. This is a quantum circuit diagram, very rough here. And other types of qubits, which we don't have time to talk about, are spins and silicon and nitrogen vacancies, et cetera, and photons, as we've mentioned. And we'll be able to use microwaves to manipulate the quantum state on the Bloch sphere to change the states and then have the qubits coupled to one another and perform calculations. When we go to these kind of qubits, because it's a quantum system, we have energy levels, and we'll be manipulating these states up and down with respect to the quantum levels. We'll get into that in more detail. But over here, you see some realizations of chips that contain qubits of this type, and we'll go into that in more detail too. We see resonators and feed lines. So there's a great deal of microwave engineering involved just to fabricate chips that represent qubits functionally, and then microwave signals that come in the standard way to manipulate and do the wonderful things using the new principles. So microwave design is key to making some of this real. Now let's look at an LC circuit and its quantum mechanical representation. So the energy of this simple linear oscillator can be written as 1/2 CV squared and the flux squared. And if we write it this way, also calling this the Hamiltonian function, the energy depends quadratically on the charge and on the flux. And formally, that looks, there's an exact analogy with the simple linear mass spring where the force is proportional to the displacement. And we know when we go from classical Hamiltonians or classical system to quantum mechanics, we replace the canonical momentum with, say, minus I h bar d by dx. It's a differential operator. And we solve the Schrodinger equation, which is an eigenvalue equation. And we get solutions at discrete values, typically, of the energy. And we know for this system, you learned this in the first quantum mechanics course, you get equally spaced levels, and this is the famous quantum harmonic oscillator. The energy difference is h bar times a frequency, which is given, not too surprisingly, by the 1 over square root of LC, as we know from circuit theory. Now, this is not yet a qubit because we have more than 2 levels, and we can't preferentially drive with microwave signals transitions between only 2 levels because we would excite all the way up the ladder. So to improve upon that, to get closer to an ideal qubit, we replace the constant inductor with a nonlinear inductor as represented by the Josephson junction, which is a sandwich of two superconducting metals around, say, an oxide, a barrier, where Cooper pairs tunnel back and forth. And that modifies the energy to make it less than quadratic. So now the potential energy is in the dark blue. And that means that the quantum mechanical levels now are non-equally spaced. And if we are careful with the frequency of our RF signals, we can stay within this two-dimensional subspace of the quantum states. And this then represents our functional qubit. It's important to note that the actual energy difference when we divide by h bar is in the gigahertz range. So this is, again, microwaves are critical. So we're in the sweet spot of RFs and microwaves. Now, given that energy difference, we have to make sure that we're operating in an environment where thermal fluctuations and other interference do not smear out the discrete nature of the quantum mechanical system. Otherwise, it would then act classically, and we get no benefits. And therefore, we need to keep the thermal energy much lower than the energy difference between the quantum states. And this says that then KT has to be much less than, sorry about the fonts, this energy separation. And given the roughly 10 gigahertz times h bar energy, it means that the operating temperature of the qubits must be down in the millikelvin, 1 to, say, 10 millikelvin. That's kind of the standard range. That's really cold. And that's colder even than outer space. Remember, there's a 3-degree background radiation from the Big Bang. 3 degrees. This is 1,000 times colder than that. Whoa. Better bring your hat. Now, to make it more tangible, this is a picture. Here's the capacitor for a Transmon qubit of this type, superconducting, one of several versions of superconducting qubits. It's got a control line for XY excitations of RF to manipulate the states. There are capacitors here to couple to resonators that will be used to read out the state after the computation, and to couple different qubits together, because you need multiple qubits to do anything useful. One qubit by itself is of no help. And then often you can route a wire to induce some additional flux and therefore change or tune the energy level separation as needed. Zooming out again, we see a 5-qubit chip of the types here, coupled to one another, coupled to the resonators used for readout, and you see the control lines for both baseband to tune the qubits and to drive the qubits with RF signals. Here's another example of a chip. This looks like a microwave design, and designing using microwave tools and methods is really critical for getting the performance. And the experimental physicists are just learning about how important this is. So there's a huge opportunity for experts in the audience to contribute here. Now, this chip sits at the bottom of a dilution refrigerator because we have to have it operate at those temperatures. And here's an example of a big dilution refrigerator hanging from the story above it. And it's got many different stages, 77 Kelvin, 4 Kelvin, liquid helium, and then ultimately down in the millikelvin range. And notice the spaghetti of cables. There are several cables per qubit. To do things useful, you need many qubits. So it's a huge routing nightmare. And if there's any problem, you have to pull up your chip, you have to open up your refrigerator, you have to find the problem, and then it takes hours to cool it back down. It's a big nightmare. And in fact, when Google did this supremacy experiment, one of their 54 qubits didn't work. It turned out there was a problem with the cable. And rather than try to fix the problem, they just tried to do their experiment using 53 of them. So it's a big problem, and scaling based on connectivity is one of the biggest challenges in scaling up qubits to the point where they're very useful, or they demonstrate the quantum advantage. Now, to give you a little more insight into how microwaves perform rotations on the Bloch sphere, we're going to show a little video. So basically, we use an arbitrary waveform generator here. We put in I and Q sequences to define pulses. We upconvert to a microwave frequency that's resonant with the energy difference between the 2-qubit levels. And then, depending on the amplitude and the phase of the I and Q, we will rotate the quantum state around the Bloch sphere in different directions around different axes. And that's how we perform all 1-qubit operations. So I'm going to play the video. We're going to start with I pulses, or in phase, and that will rotate us around the x-axis in one way, then the other, down here, then around the y-axis, all the way down to the south pole, which is the other state, and then halfway down. So here we go. Let's see if it works. Okay, the first rotation around x, we're down at the one state. Going the opposite way, we're back. Around the y-axis, we also get down to the bottom state. And now we rotate halfway to the xy plane and another halfway. And we don't have to do it halfway. We can do any combination. So with different I's and Q's, we can get from any point on the sphere to any other point. So that's the idea. Again, the frequency of the RF is the same as the qubit. Now, here's an example of what we call a quantum circuit. This is how you would read an algorithm. This is one case where we have only one qubit. We prepare it in the ground state, and we can wait for it to decay because it's lower energy. And then we perform a pulse. And if we do one of the pulses that I just showed you, the first blue one, we will be rotating around the x-axis, and we end up at the bottom of the Bloch sphere in the other basis state. And then if we do that again, same pulse, carefully synchronized, in phase, we'll get back to 0. And we see we are effectively swapping the two basis states. And in terms of coordinates, there's a matrix that represents that action, and it's just the NOT gate. Very simple matrix that's invertible, that swaps the different basis states. And these are the symbols for 1-qubit gates, and X gate is one of many possible gates. If we go halfway, as we saw in the video, in the animation, we end up in the equator, and that is how we do the superposition. So we can manufacture or put the qubit into a superposition state by doing a rotation either again at the same qubit frequency at either half the time or half the amplitude. And then if we were to apply the same pulse, but we didn't quite get it in phase, and so it's now 90 degrees out of phase, we'd be rotating around the y-axis. But given the state here, we're already along the y-axis, so nothing happens in this case, and we stay in the superposition case. So it's important when we actually effect these transformations that we have a clean clock, and we have to do this quickly while the qubit still lives. We'll talk about decay of the qubit soon. And now, and this is a typical experiment that the scientists do to make sure everything is running. You excite the qubit at its resonance frequency, and you then, at a small time interval, you take a measurement. You see what, if you start at 0, you measure it a short time later and determine whether the qubit that you've measured is still in 0 or has it given you the one answer. Remember, there are only two possibilities. And then you do it again at the same time, and you'll get a different answer. But if you do it thousands of times at each different time interval, you will build up the probability of getting a 1 starting from 0, and it will oscillate like this. And these are the so-called famous Rabi oscillations. And a qubit has to be able to do this if everything is working properly. So this is typically what's done. And even the frequency of the excitation is adjusted to get this working properly. But in reality, if you perform this experiment, instead of this ideal result, you get something that looks more like this, where the probability doesn't reach 1 anymore after time, and ultimately the qubit decays because it interacts with the environment that's undesirable for everything except a sensor, and the relative phase of the superposition decays. That's called dephasing, and then the energy relaxes as things fall to the ground state. So the qubit has a very short lifetime typically. It depends on the technology. For superconductors, it's been increasing dramatically, but it's still, as far as I know, less than 200 microseconds. So we have to be very efficient in manipulating qubits while they still last. Get them while they last. Now, I haven't said anything so far about how any of this manipulation with microwaves enables a benefit. To get a benefit, as I alluded to, you need multiple qubits. And so if I look at a 2-qubit state, it's a superposition in 4 dimensions. The bases can be written in terms of the states of either qubit. So qubit A or 1 is the first one, and qubit B or 2 is the second. And one kind of state where the coefficients of 2 of the superposition terms are 1 looks like this. Since 0 appears for the second qubit in both parts of the superposition, it can be factored out. And in this case, whatever measurement you do on one qubit tells you absolutely nothing about the properties of the second and vice versa. So that's not too interesting. That's like a classical state. But then there are these superpositions where it's just C1 and C4 that are unity, and this particular superposition of a 2-qubit state is what's known as entangled. In fact, it's the maximally entangled Bell state, of which there are 4. And what's amazing, and has perturbed people back from Einstein's time, is that it induces incredible long-range correlations that can't be explained by any classical theory. So in particular, since it's a superposition, if we were to measure 1 qubit, we would collapse the wave function, and we get either the state 0, 0, or 1. So if we measure a 0, we know that we have this state. And if we measure a 1 of either qubit, we know we have this state. But once we have either one of these states, and we've measured only one of the qubits, we know the other one has to be in the same state even without measuring it, and even if that qubit is halfway across the universe. So in particular, if we prepare 2 qubits, they're 2 distinct entities, but they are entangled in this way, and we send one across the universe, we measure qubit 1 in our lab, we know immediately and instantaneously the state of any measurement that would be made halfway across the universe. And we're not doing that to the other qubit, as some people would think. We're not, but if we were to compare notes later or send light signals and information, we would be able to see 100% correlation in the measurement results. And the importance of this is that it's possible to use entanglement as a computational resource. We said we could only extract a classical bit from a single qubit. It turns out you can extract or encode 2 classical bits of information in a single qubit if it's part of an entangled pair. And this is used all the time. And you need to use entanglement to get any quantum benefit. Now, if we go to 3 qubits, if we go to 3 qubits, we have a superposition in 2 to the 3rd dimensions. So by induction, n qubits live in a 2 to the n dimensional space. It's incredibly complicated. So if there are estimated to be 10 to the 80 particles in the entire universe, if you solve that for 2 to the n, you get n is about 270. Sorry for the fonts. And basically, it says that with less than 300 qubits, there are more states accessible for computational purposes than there are atoms in the universe. And people would use this as a hand-waving argument to say, even if every atom were dedicated to classical computation, you would get more power out of only 270 to 300 qubits if they were ideal and didn't decohere. And so we want to try to approach that. Now, I said it takes 2 or more qubits with entanglement to get any benefit. So I won't go into the details of how we do that with signals. It's complicated. But we talked about the matrix of the NOT gate. The operators on 2-qubit states, since they live in 4 dimensions, are matrices. Quantum mechanics is linear. And notice the subblock is the NOT state, is the NOT operator. And this is called a controlled NOT, or CNOT gate. And it permutes the basis elements according to this. So if the first bit is 1, the target bit will be flipped. And the circuit diagram, now we have 2 qubits. So x and y can take binary value 0 or 1. And you get out here, say, the addition modulo 2 value of the answer here. And simply by using an output that maintains one of the inputs, this is a quantum gate, 2-qubit gate, that is a representation of the classical exclusive OR gate in a reversible way. So you do this again, you get back x and y. Another thing I'm just going to mention quickly is that any classical logical function can be implemented quantum mechanically by extending the logic to a reversible logic, sometimes by adding additional register. And that's necessary to maintain the unitarity of the quantum transformation, namely you're rotating, preserving the length of the quantum transformation that has to be invertible. And that is possible. There's a theorem that says with only this 2-particle or 2-qubit gate, then using this gate and all the available single-qubit rotations on the Bloch sphere, any possible quantum mechanical transition for n qubits is synthesizable. So we have the basis for any computation. Now I want to go to readout, and we'll do this quickly. After a computation, we want to establish what the value of the measurement is, or the state of the qubit. And we do that by coupling the qubit to a resonator, and then we send in a pulse. It could be, it's an RF pulse, and we look for, say, the resonance output, or the dip in magnitude, or in this case, or the change in phase of a transmission measurement, another microwave measurement. Now, we typically send in a pulse for the readout resonator at a higher frequency. The resonator is roughly, say, a gigahertz away from the qubit energy. That's a coupling regime that is useful. And it turns out that because of the coupling between the photons in the resonator and the qubits, the state of the qubit pulls the resonance frequency left or right a little bit of what the resonator would otherwise be. And so by measuring the transmission, we can determine the state of the qubit. It's as if the dielectric constant of a capacitor depended on the state of the qubit, or different material. So that's kind of a hand-wavy argument, but this is how it's done. Again, we have to make these measurements very quickly in order to get useful information before the qubits in the experiment or in the computation decohere. So let me give you a quick sense about quantum algorithms, where we can put all this machinery together and some of these basic principles. So we look to amplify the quantum amplitudes. We'll need to do some error correction, and interference, which is related to superposition but a little different, is a key concept. So look out for those. And this is due to the fact that in quantum mechanics, probabilities, which we talked about, are inherent, but they're not the most fundamental aspect. In quantum mechanics, they're the probability amplitudes. Those are the complex numbers in a superposition. And if there are two distinct ways in which something can happen, in quantum mechanics, you add the amplitudes for those mutually exclusive events to get a total complex number, and the probability that that event can happen is the absolute square of the sum of the amplitudes. And then expanding that, we get the classical result, which said simply that the probability for two mutually exclusive events is the sum of the probability. But there's a new term. There's an interference term. And that says then that depending on the relative phase of the quantum amplitudes, you can have the event not happen. And so this quote really says it all. It's possible if there, one way it can happen and another way it can happen, that due to interference, an event may not happen at all. That's non-classical. Of course, you can turn it around and say, suppose we can get constructive interference, then we have a higher probability that the event can happen, and that's key. And here's a nice conceptual diagram of how that works, courtesy of MIT. So we take, in this case, a 3-qubit state system to illustrate it. So 3, we know, has 8 basis states, but we're only showing 4 of them. We take each qubit and manipulate it with a pi pulse with microwaves, and that forms an equal superposition of all of the basis states, so they have the same amplitude. Now, if we were to measure the qubits here, we would get randomly one of the 8 possibilities with equal probability. But if we're clever, and here's where the genius is of some of the theorists who came up with some of these algorithms, you start manipulating the qubits on the block spheres with microwaves, and then let that interfere with each other. So the superpositions evolve in time. The Schrodinger equation is a unitary evolution. You don't look. You have to hide your eyes. You don't want to query this or you'll collapse and destroy the interference. So you let it do its thing, and then you do some of these controlled NOT gates to entangle the qubits and let it evolve like a wave system, which it is. It's a wave mechanics. Ultimately, if you can determine the sequences of these operations, the idea is to try to constructively interfere one of the coefficients to become close to 1, and then, since the sum of the squares have to be 1, the rest of the amplitudes are suppressed. So at the end of the algorithm, you make a measurement, and the measurement, we said, is then proportional to the absolute square of the amplitude. And if the amplitude is approximately 1, you're very, very likely to get the correct answer. Again, the genius is in how you do this and how you take a problem and code it and provide microwave pulses. Unfortunately, I can't go into the details. You can see me later if you want. So that's the idea. So in the end, a quantum algorithm written in terms of different symbols for single qubit gates. So each gate that's on one line is a single qubit operation, like we saw. These symbols are different kinds of 2-qubit gates that can all be manufactured out of the CNOT and other single qubit gates. In the end, it's nothing but a set of microwave pulses, carefully synchronized, provided very quickly, and because of the decoherence, we have to do this quickly with many different highly synchronized pulses in time, and maybe also some of these Z-control baseband pulses to tune resonance and make different qubits resonate with one another. We have to do this within the short lifetime of the qubits and do this all at fantastically cold temperatures. And because the error rates, both in the signals we use in preparing the states and in affecting the quantum gates, are significant, they're high compared to classical error rates for transistors, which are at least 8 orders of magnitude lower, we have to do quantum error correction. And that's another of the many enormous challenges to making this practical. So let me give you a brief indication of how error correction is done. So typically, we use redundancy. That's a standard strategy. So instead of 1 qubit, we assume the error rates are small enough that we can represent a logical qubit, say the effective 0 and 1 state, by one of these 2 3-qubit states. So any superposition of this basis state or this state and that state represents a logical qubit, and then we do the same thing. We do these operations on the logical representation. If we were to ever query the qubits and they happen to be in this state, which is a fine state for 3 physical qubits, we'd know we'd have an error. We're outside this 2-dimensional subspace. And so we have to correct it by, in this case, say, doing a majority vote. So this state would be corrected to 111, and if we got this state, we would correct it back to 0. So we stay in this logical 2-dimensional space. So there are all kinds of fascinating ways that this can happen. And we take the 3 physical states, and then we entangle, using our CNOT gate, 2 additional qubits with the physical qubits. And then we measure the state of the ancilla, or these additional qubits. And that collapses the entanglement. And by making the measurements, again, 0, 1 are the only possibility for each one, so we have 4 possible outputs, it's possible to infer which qubit, which physical qubit had the error, and then provide the correct single qubit operation to correct the error. And the key here is you can do this without even knowing the state of the qubit. If you were to actually query the state of the qubit, you destroy the coherence and you wouldn't be able to do anything. It's a parity operator. So this entanglement just basically identifies which qubit is not the same as the other ones, even though it doesn't tell you anything about the qubit state. And then you can provide, if you can make the measurements quickly enough, the right pulse to make the correction. And that requires a very low latency digitization, the ability to launch pulses on different qubits very quickly and with high fidelity to make these decisions, because you never know what you're going to get. The error might, you do it here, the error might be in the second qubit, and you have to then correct that one. So you need real-time feedback and well-controlled microwave pulses. Now, unfortunately, because the relatively high error rates now, the typical value of redundancy is on the order of 1,000. So to do anything really practical, you need millions of qubits to do something useful. So there is a threshold that is getting reduced. We're getting closer and closer to where quantum error correction can actually be made to be practical. We're not there yet, although there has been a recent experiment, maybe it was the Google group also, where they've demonstrated that they can do certain experiments and they actually get a benefit from some of the error correction. But it's not a practical tool yet, and still a topic of detailed advanced research. So let me conclude now and say that I hope to have demonstrated that the microwave aspects of quantum computing are really key to practically realizing this technology for the future in terms of reading out, manipulating, and correcting the quantum systems for computation. There's a huge amount of progress. So it's not just hype. There's real progress, lots of money, lots of great research, and that it's coming out of the physics labs. It's not just a curiosity. It's becoming a full-scaled sub-discipline of engineering, and there's a huge opportunity for the IEEE. There's a new quantum community for microwave engineers in particular to work with physics. There are master's programs where you learn microwave engineering and quantum physics. It's very vital. It's a great opportunity, and I can sure say it's extremely exciting to work in this field. So thank you for your attention. I appreciate it.
Thanks very much, David. That's actually the best description of all of those works that I've seen, that I've listened to a number of them, so I really appreciate it.
Thank you.
I guess I'm wondering, somebody was to ask you, why can't you do this? Why aren't you doing this with optics or some other approach? Why do you need to do this with microwaves? How would you answer that question?
Okay, first, thank you for the previous comment. You don't need to do it with microwaves. Optics is a little bit different because you have to generate entanglement in different ways. So to entangle photons, photons are perfectly good qubits, but they don't like to stick around. They like to fly away. They are long-lived, though. You have to generate them by some mechanism. Typically, it's parametric down conversion. You shine a laser at a crystal, and it will split a high-energy photon into two entangled photons at different energies. And so the qubits based on photons are viable. And then, but you may want to use photons, and I think this is what most people think. You use photons to transmit quantum information from certain solid-state qubit systems, say spins or superconducting qubits, so that you can transmit the quantum information from one site non-locally to the other. The Chinese have done this with the satellites. So photons are great for communicating. They're harder to keep around, they're harder to manipulate, and they're potentially harder to generate, although there's a lot of work now generating photons on demand that are entangled. I think most people are looking to use multiple technologies, have them interact in different ways, and transmute information back and forth, architecting systems. Maybe the cores will be solid state, the memory will be a different technology, and the inter-core communication photons are good candidates, as are phonons and other quantum systems. Did that partially answer your question?